And we have some other data that says as the longer you look at a video, the longer you listen to audio, after the first 20 minutes, you don't find as many things as you do in the first 20 minutes looking at it. You get bored. Your attention wanders. The AI attention does not wander. It's a machine. So it can work forever. And so we can automate a lot of tasks. And that's a large majority of what we're doing. And you'll see some of that later. And then we can verify the nature of an activity. So we can double check, right? If there's an incident occurring, like a fire or a big traffic accident or some other thing, there's a lot of things going on. Humans are very good at reacting and doing this in real time. It takes a lot of experience. There's not a lot of experience out there. So AI can accelerate our understanding of a real-time event. And so that's a portion of what we do. And then assist. So afterwards, or how we adapt, we can assist a person in their task, or we can assist somebody after the fact to help them determine what happened and make it better for the next time. So how do we use this at Motorola, right? So I mentioned that Motorola provides software, not just radios. We provide software in the command center, and our software does things like it helps. In the U.S. it's 911, in other places it's 999 or 111 or whatever it is. So when there's an emergency, citizen calls in, we have call taking software that helps that. So there's a couple of roles there. During, say there's a traffic accident and we have to dispatch units, right? So we have a dispatcher that says, okay, these two fire trucks go and this police officer goes. If there's some kind of riots or some other type of an incident, we can have an intelligence analyst looking at cameras and trying to assist the dispatcher and assist the first responders. We have first responders. These are the police and fire and EMS, emergency, ambulance drivers, things like that. And then afterwards, we need to understand what happened, and we need to solve crimes, and we need to analyze. And so we have, at Motorola, we have software to help all of these people do their jobs. And we refer to this as like an end-to-end workflow. Citizen calls in, call taker talks to the citizen, creates an incident, dispatcher sends the units. Depending on the incident, there may be an intelligence analyst working in real time. The frontline responders are actually in the field doing their job. And then afterwards, records are created and we analyze what happened and follow up. And so how does AI help here? And so this is where we talk about how what we're doing at Motorola to leverage AI. And we have David and is going to talk about this later on how we can automatically transcribe, do speech to text on 911 calls in real time as they come in. And so we can identify terms. We can make recommendations. So this is a very important part of what we can do to assist the call taker in doing their job. And also do more detailed analysis afterwards. Quality. How'd the call go? Were people too stressed out? Can we do better next time? AI can help dispatchers by making recommendations. Right? Maybe there's a closer unit, and hey, you know what? There's a unit over here that's not doing anything. You sent this one. I mean, you might want to send this one. Well, dispatcher can make that decision, but the AI is doing the recommendation, and they notice something. And I mentioned video and watching video and looking at an incident in real time. We can look at cameras that humans are not looking at. Maybe look for smoke. Maybe people where they're not supposed to be. Maybe somebody left a bag outside an airport terminal. These are all things that AI can help recognize in video. So many cameras. There's just no way people can look at them all the time. So that can happen in real time or it can happen afterwards. Another thing that you're going to see a demonstration of in another presentation today is a digital assistant, virtual assistant. We have Siri, we have Alexa, we have Google. We are providing that technology to police officers in the field to look up information, dictate reports, things like that. That allows them to do their job faster. It keeps them safer because if they're not looking at a screen or writing something down, they can keep their eyes on the situation. So they use their voice instead of using their hands. Very important for safety. And then afterwards, in the post-incident area, we can help AI just save time and speed up either data entry because we can automate things, or we can speed up solving crimes or things like that, where we can search for video, for example, search databases, get more information in the detective's hands or the analyst's hands, and this actually we can point to improved prosecution rates and faster resolution to things by using these techniques. That's actually something we've been able to show. And so there's one more point I want to mention on AI at Motorola. I kind of said, AI we can take it too far, and we're not anywhere close to having the type of artificial intelligence that is like a human. And so we want to make sure that we have a human in the loop. We want to make sure our AI applications are ethical. And so essentially what we're doing, it helps the person make better decisions. It does not make the decision for you. We don't automatically send units with AI. We recommend what units to send. And then the human can make the decision on if that's a good recommendation or not. And by the way, since it's machine learning, if the human says no, well, the recommendation may change the next time, right? That's how the machine learns. We focus this. So we have very focused use cases. I want to use my voice to look up a license plate. That's a very, very simple thing, very straightforward. It's very easy to understand. If AI is gray and the users don't know what it's doing, they're less likely to use it, and it'll cause more problems than it'll help solve. And then also it's mature, right? So we're not on the bleeding edge in public safety. Our customers are very it's mission critical. Mistakes cost lives, and so we use well-established techniques and in the industry to apply those to public safety. And you'll see, the engineers will talk about what some of those techniques are. So in summary, data is everywhere. There's too much data in the world for us as consumers and citizens to function without assistance. And so AI is in our lives. I mentioned Alexa and things like that. I use that all the time. And also for our customers at Motorola, public safety, police officers, fire, EMS, etc. And there's tremendous potential here. We're just starting to scratch the surface. We can automate mundane tasks. We can accelerate workflows. We can assist from the time the citizen calls to the time the case is closed. And we never lose sight of the fact that this is a great tool, but we must use it responsibly. There's too many examples of AI doing the wrong thing. We don't want that to be Motorola. It can hurt reputation. It can harm our customers as well. So we're very careful on how we apply AI to our products. So that's our introduction to what we do and how, at a very high level of how we apply artificial intelligence and machine learning to our products. And that's the end of my presentation. So hopefully the rest of the session, you can dive in and get some more details on how some of this stuff actually works.
Okay, so we are in a Q&A session. If there's anyone who has questions to Rick, please go ahead. The stage is yours. Okay, we have okay, I can see that for video analysis, which technology is being used. I can see it in chat, so probably somebody can only type. Rick, can you see it in the chat?
Yes, I can see it. So you can still hear me, right?
Yep.
Yeah, okay. So I think David might actually be able to answer this better, but the technology we use is we built it ourselves. So there may be some foundations and some open source or something, but we've created our own algorithms. We have some algorithms built into cameras directly. We have other algorithms that run in the cloud to process video. It's homegrown. Motorola's developed it.
Can you guys hear me?
Yeah, go ahead.
Okay. Hey. So as Rick said, there's not one thing, right? So as he said, on the cameras, we actually use a custom model. It's essentially a SSD, so it's a single shot detector, but it's built in-house by us. The reason we build it is we have to actually make sure that the compute footprint fits with the AI SoCs that we use on our cameras. That said, in the cloud and other places, we have lots of different other network architectures we use. Some of them are adapted from, well-known models from, academia. Some of them are built ourselves. So there's basically no one answer for that. If you think about the type of video that Motorola deals with, that Rick, pointed out, there's fixed video, there is mobile video, where the not only is obviously subjects moving, but the camera is moving as well. And so you need, we have to support different pixels on target. We have to support, different types of tracking and things like that. So there's basically a variety of different models that we use for machine learning and video. And I think one of the future sessions will go into that a bit more.
There's another question about the voice sentiment analysis in Vicky. So Vicky's a product that we launched. That's our virtual assistant. You can go learn about it at motorolasolutions.com. We currently do not do sentiment analysis, but it is something that we're looking at doing, and we understand the techniques that we would need to do. Vicky itself is it's a simple, well, it's not simple. It's actually quite complex, but it's a conversational bot. So within the conversation, it's just the data we're interested in. What do I intend to do, and what, if I intend to look up a license plate, I need to know the state and number. When we have transcription, like for 911 calls, that's where sentiment analysis would be much more valuable. We can detect the sentiment of the call taker. Are they stressed? We can detect the sentiment of the caller. Are they lying maybe, or there's something they're not saying? Are they in a situation where they can't speak everything? They can't, they can't tell you what they want to, because somebody is standing there listening. So there is definitely a role for sentiment analysis in what we do in public safety, and it's something that we're considering moving forward.
I can see there are more and more questions. So Rick, just take two, and if you're gonna have more questions, we have a separate email. You can drop it over there. I'm gonna reply to it.
Yeah, we have just to address Tom's question. We run on Azure, Microsoft Cloud Infrastructure. We do a lot of our own services on top of that to make it compliant with public safety regulations, and we use things like Kubernetes clusters to run a lot of our compute. And there's one more. I think I have time for one more here. How is the real-time interaction, and how do we take the decision in terms of AI, ML, motion detection, and things? So there's we apply these techniques in two ways. We do a lot of batch processing or post analysis, so we can take large video files and audio files and transcribe them, detect things in them, and then put that data in a searchable database where we can extract information or do analytics on later. From a real-time perspective, we do real-time detection of audio today and in video, right, where we can detect a license plate in real time and other objects and alert. We can run searches and queries, and so that is definitely things that we do. So the algorithm will make the decision. It'll detect something, and then you have to have associated action, right? So if I see a license plate, what do? I identify license plate. So what? Well, I need to run a query. Is the car stolen? Or it's a simpler thing. As soon as I detect smoke, I display the video on the screen in the command center with the big red flashing title or something. So there's today we do have real-time use cases in terms of detection on video, and obviously we're just starting with this technology, and more things will come in the future. But it's very important to define that action. And remember what I said before: we don't want to just take action. We want to make recommendations, because if we take an action and it's wrong, that's a bad thing. I don't know the answer to the real-time language. Maybe one of the engineers can step in. But while somebody's thinking about that, in the future, will AI be able to handle all incidents, or human people will always be required? That's the big question, right? I think for the foreseeable future, and I'm a big science fiction fan, and I love reading and watching movies and things. We believe we're always going to need a human. If it's life or death situation, we're just not in a position to automate decisions. And that's okay, because if you make the recommendation and the recommendations are good over time, people will trust the recommendations and trust the machine learning. And instead of questioning the recommendation, they can see very quickly if it's a good one or a bad one. And so I think there's, for the foreseeable future, at least in our business, we will have a human.
Okay, I think that we can move on yet again. If you're going to have more questions, you can always send them to us, and we'll be more than happy to answer. And as for the next topic, it's going to be Grzegorz. The stage is yours.
Hello, can you hear me?
Yes, we can.
Okay, so let me just share my screen. Okay, can you see it?
Yes.
All right, so let's talk about virtual digital assistants. And let's imagine that this box on this slide is such a virtual assistant. One of those that you can ask to tell you a joke, and it will hear you using voice recognition, and it will grant your request. You can ask it to turn on the lights or to play your favorite song. And let's take this idea to the public safety land. And imagine that there is an abandoned car parked near a road, and a police officer is called to investigate it. And he doesn't really know much about the car, but he can read the license plate. So imagine that he has such an assistant, and he can pull out his radio and say something like, "Hey, Vicky.
Go ahead.
Check New York license plate, November 323, Bravo, Romeo."
New York license plate November 323 Bravo Romeo. Is that correct?
Yes.
Searching. Results available.
Go ahead.
Warrant for arrest for Stan Mustang in Florida. 2007, BLK, INFIG 35, reported stolen. Driver's license valid. Request more information or say complete.
Complete, thank you. And thanks to this assistant, the officer knows that the car is stolen and there is a warrant for arrest for its owner. And this is exactly what Motorola Vicky is about. It is a virtual assistant built exclusively with public safety in mind. And today it can check a license plate, driver's license, vehicle identification number, and either own or other unit's location. And I'd like to talk a little bit about designing Vicky, especially in the context of the artificial intelligence and machine learning services, which we are consumers of. So as you may have noticed, Vicky is not an ordinary web application. A typical web application accepts a well-structured input, for example, a JSON document, processes it and returns a well-structured output. This may be a JSON document as well. Vicky, on the other hand, listens and speaks. So in other words, In other words, it uses voice in communication, which alone leads to some interesting challenges in its design. The first one being how to teach Wiki to listen. Because, as I said, the input to Wiki is a voice recording from the radio. And to help us with that, we used Microsoft Azure Speech Service and exactly the custom speech feature. And the way it works is really simple. We just send it an audio recording, and we get back a transcript of that recording in a textual format. And in our case, this is based on our own custom acoustic model, which we can train by feeding the custom speech feature a bunch of WAV files together with a textual file containing the transcripts for each of those files. And we needed to train that model very hard, and we needed a custom acoustic model because of our specific situation. I mean, the police officers talking to Wiki via a radio can be in a very noisy place, for example, where there is a lot of traffic. And also, the police radios tend to have a relatively low bit rate, which limits the audio information that is available to the recognition mechanisms. So we needed to train that model to avoid situations like Quebec being recognized as good back, or Nebraska being recognized as in Nebraska. And thanks to the extensive training and using the custom model, we were able to raise the accuracy. And the other thing we did was dropping the alphabet when spelling, for example, license plates. So instead of NBR, our users say November Bravo Romeo, which are NATO alpha codes that are well known by the police officers. And switching from the alphabet to NATO codes allowed us to raise the accuracy level even higher. So thanks to all of this, we managed to solve this challenge of teaching Wiki how to listen. But listening alone isn't enough. Wiki needs to understand what its users want, because someone might say, check license plate. Another person might say, run a plate. And the next person can say, got any info on this plate. And each of those cases, Wiki needs to know that the user is asking to check a license plate. So to do that, we are using Microsoft Language Understanding service called LUIS. And similarly to custom speech, LUIS has its own model that we can train. So we can give it a phrase, for example, run a plate, New York, Alpha, Bravo, Charlie, 1, 2, 3. And we can mark the word plate as an entity of type license plate. We can mark the words New York as an entity of type state. We can mark Alpha, Bravo, and Charlie as entities of type alpha code, and 1 and 2 and 3 as entities of type number. And we can tell LUIS, if you ever encounter a phrase like that, recognize it as a license plate query, extract all of these entities, and present it to us in a structured format so that our computer program can consume it in a deterministic way. So training LUIS might seem like an easy task. However, there are some quirks we needed to work around or deal with. And for example, a user may say license plate 123 Alaska. And Louis should recognize this as a new license plate check. But on the other hand, a user might just say 123 Alaska, and this should be recognized as missing query parameters. So note how the second sentence is a subset of the first one, but we need to detect it as a totally different intent. So teaching Louis to distinguish between cases like that took us some time. Another example was when Vicky was trying to confirm the query parameters. So if we issue a query, Vicky asks, Alaska 123, is that correct? Because this is what I understood. And we can correct that. We can say, no, New York, instead of Alaska. And Louis understands no with a dot as an abbreviation for the word number. So it recognized the sentence as number New York, which led to the wrong intent being recognized. So again, we needed to work on training the Louis model to get that right. Anyway, by doing Louis, we achieved our second objective, which was to allow Vicky to understand what the users want, and then we could process this data and act on it. And the last task that was left to solve was to make Vicky speak. So we already knew how to turn the input voice into text. We already knew how to extract some structure from the text. And now we needed to focus on sending a response as an audio. So to do that, we used a speech service from Microsoft, but a different feature that's called text-to-speech. And it works very similarly to custom speech, only that while custom speech accepts audio and returns back a textual transcript, text-to-speech works the other way around. So it accepts text and returns audio. And the text-to-speech service also has a model that we can train, although we don't do that. For text-to-speech, we just took one of the default ones. However, we still needed to influence how the voice is synthesized in some places. For example, if we pass to the service an address like this, S. Clinton ST, which is South Clinton Street, then the text-to-speech service will just convert it literally to speech. So it will convert it to an audio that will say S. Clinton ST, which is not what we would want. So we used a feature of text-to-speech service called SSML that allowed us to annotate some of the text with tags that specifies how the text should be interpreted. And then the text-to-speech service was able to give us the correct audio. And thanks to the text-to-speech feature, we were able to solve our last challenge, which was teaching Vicky how to speak. So just to summarize, we have three big challenges: teaching Vicky how to listen, teaching Vicky how to understand what the users want, and teaching Vicky how to speak. And for all of them, we used external Microsoft services built on the artificial intelligence and machine learning concepts to help us with these tasks. And in two of them, we use custom models. And thanks to all of these services, and thanks to using them, we managed to make Wiki a full-fledged product that can be reliable partner and assistant to a police officer like the one called to an abandoned car. Thank you.
Thank you, Gregor. So yet again, I can see that there are some questions on chat, but if any of you have questions about Wiki, go ahead. We're open and more than happy to help out.
I think I can see one question. Does Luis know Japanese or Chinese language and symbols? Frankly, I don't know. We only use English with that one.
Yeah, Gregor, it does. We've only implemented English to date, but Microsoft supports simplified Chinese characters, and I placed the link in there. You can go look at their website and see what's supported. There's some other notes about Chinese and Japanese language support in general for Lewis, but today we run English. We're looking at some other languages.
Cool.
Okay, there is another question.
Do you consider extending Wiki with image from on-body camera analysis? It may help in case when officers should keep silence. I think that questions about future plans, I think Rick would be the better person to answer.
Yeah, this is the benefit of the amount of data that we have in real time at Motorola through radio traffic, cameras, things like that. There's lots of ideas on how to combine that. You might have noticed in the presentation in terms of when an officer should keep silent, there was 3 beeps before, and then the Wiki said results are available. Wiki didn't say the results, what they were, so we don't know what the officer's doing. There may be somebody standing there and you don't want to say the result because there's private information. You might tip off a suspect. And so the nature of the beeps themselves will let the officer know. 3 beeps meant there was a warrant or something. 1 beep would have been no interesting information. So the officer doesn't even have to ask for a result. They may change their action based on the beeps. So that's a case where we understand in the field that the officer may be in a situation where saying too much information would be a bad thing. We have all kinds of ideas about using cameras to detect objects or read license plates or driver's license and things like that. That we look at for the future. We ask police officers what's important to them, and we do research and things like that. But right now, we don't take any data from real-time camera to assist Wiki.
Okay. There is another question. The results are trimmed to context like geolocation. So not currently. I mean, the user, for example, when querying police or government databases, has to tell the state for which they are asking, but this is about the number, not about his own location. We do support location feature, but that's for getting our own location. So the user may ask, where am I? And for example, they can ask, where is unit X or where is unit alpha 2? So the location is given. Other than that, we don't use geolocation in other ways. For real-time data analysis, is there some optimizations done with Luis on Azure, or is it tailor-made for fast analysis? So we don't do any optimizations, that's for sure. What Microsoft does with it, I'm not aware of anything like that. So we don't do any special optimizations for Luis. Does Motorola have watches monitoring police officer heartbeat, etc. in case phone was not available? I think, Rick, could you chime in on
Sure.
that?
We do a lot of monitoring of police officers' equipment. We have a service called Responder Alert. I will put a brochure in the link. Check it out. There's things like weapon drawn, vest piercing, and other things on the body of the police officer. Potentially, we could add heart rate monitors and biometrics and things like that to that system. That's not something we do today. There's privacy things, and it's a sensitive topic. But we do a lot of monitoring of the police officer through sensors on the body, and you can check it out in that brochure that's on our website.
Okay.
I think that there are no more questions. Oh, Tom is typing something. Is it going to be a question? I think that we have some more minutes, so.
Okay. I think this is about the continuation of the previous question about monitoring police officer heartbeat and so on.
Yes, it is a continuation. So, Rick?
Yeah, we spend a lot of time in general on use cases for fire. In fact, we're working on some things for Vicky, and also we can search for premises hazards, like if there's dangerous chemicals in a buildings or things like that. Currently, we don't have temperature sensors and things that would do something that specific, but we definitely pay a lot of attention to the fire market and the firemen and women that are out there. How can we make them safer? What data can they get on the way to the scene? How can dispatch assist them with information? And so it's maybe less of a machine learning AI than it is a response in terms of this type. Well, we could apply AI like this type of fire in the past required this specialized unit. I make a recommendation to the dispatcher, and that can be determined through cameras. It can be determined through other data that comes in. And so it's more about getting the right units on the scene, getting the information to the response team on what the building is, what's in the building, any other interesting facts about it. Did any different alarms trigger, I think, and things like that. But on-body sensors that detect temperature and other chemicals, it's a little bit out in the future for us.
Does that answer your question, Tom? Okay, I think that we can move on to.
All right.
To
Thank
the
you
final.
very much.
Thank you, Gregor. To the final presentation. So I wanted to welcome David and Maciej. Please go ahead, gentlemen.
Thanks. So presumably you can see me and hear me. Sure, okay.
Yes, we can.
Great. So I am David Calico. I'm the team lead of the speech and audio team in the Chief Technology Office at Motorola Solutions. We work on a lot of projects like sound classification, and what I'll talk about today is transcription. And the title of this talk is Building AI to Intelligently Transcribe Emergency Calls. So in this talk, I'm going to talk about first how the underlying artificial intelligence transcription model actually works, like the guts underneath it, because I think it's pretty interesting. And then I'll describe how research scientists at Motorola train public safety specific transcription models, not just something off the shelf that you could purchase from a company, for example. And we'll conclude with a demonstration of the actual product that we are selling today called 911 Smart Transcription. And what that product looks like is, you can see in this picture, this is a call taker in a public safety answering point. She is answering 911 calls, and she's also doing many other things at the same time. Usually these pictures are showing 5 or 6 different monitors and 3 or 4 different keyboards that these people are dealing with all at the same time. And on the right side of her screen, it's a little hard to see, but there is a rolling transcript, which is describing is transcribing what she is saying and also what the caller is saying. And they use this because there are so many things going on. If the caller says something and maybe they don't remember it, they can glance down at the transcript and they can refer to it. So rather than asking the caller to repeat the address that they just said, they can instead ask, did you say 123 Fake Street? And the caller can just say yes or no. And there's other benefits which will be talked about later, but searching past transcripts, things like that. But let's get into it. So transcription, the way it works is that it starts with a waveform, an audio waveform, which you are familiar with. And this waveform is converted with some Fourier transforms into an image, which is called a spectrogram. So this is a spectrogram here. And on the y-axis of a spectrogram is frequency, and on the x-axis is time. So time is increasing from left to right. And the sort of vertical gaps that you see, there's 3 or 4 vertical gaps. This is because this spectrogram is someone saying a few words, and the gaps are the spaces between words. So that's in the time axis. And the shapes that you see along the frequency axis, this is just the different frequency components of the individual words that are being said. And that is caused by the changing shape of your vocal cords as you speak. And so different words have different sort of visual characteristics in this image. So interestingly, transcription, even though it's an audio problem, is at its heart an image recognition problem. Okay, so from this spectrogram image, we extract some extra features, which for the sake of this presentation aren't really relevant. You can just imagine a picture. And this picture is fed into 3 critical components. There is an acoustic model, there is a language model, and the acoustic and the language model are combined in a process called decoding. So we call that a decoder. And what comes out is a sentence. So for example, if you start with this waveform, you get the spectrogram. What comes out is a sentence which might be, thank you for listening. And that's sort of the big picture. And what I'll do now is go through the details of each of the different components and how they all fit together. So what is an acoustic model? An acoustic model is, in general, it's a neural network model, machine learned. And what it learns are the acoustic characteristics of the audio. So if I record the same audio in 3 or 4 different environments, maybe one of them is on a phone, one of them is a high quality microphone, one of them is on a radio, one of them is outside with cars driving nearby, the spectrograms look very different, even though the words are the same, because they come from different acoustic environments. So when you are training an acoustic model, you need to train it on spectrogram images which come from the acoustic environment that you're going to eventually care about transcribing. So in this case, we care about emergency calls. So we learn the acoustic characteristics of emergency phone calls. We generate these spectrogram images and we train our machine learning model. Oops, sorry. So an acoustic model is trained on both audio and human transcripts. So what you're handing this machine learning model are audio files, but also, so you're handing it spectrogram images, which come from audio files, and also for each image, what words were actually said in that image. And then the machine learning model is learning to correlate those 2 things. And like I mentioned before, it's highly impacted by acoustic characteristics, hence the name acoustic model. So if we dive back into this spectrogram image that I was showing earlier, where the sentence is, thank you for listening, the acoustic model, which has been trained, may look at this and may identify, okay, these are the vertical gaps. This is where the spaces between the words are. And based on this subset of the image, I think that word is thank. I've been trained on a lot of spectrogram images, and I know that the word thank usually looks something like this. And I'm 50% sure that it is thank. But I'm 10% sure it's plank. Maybe it's think. Maybe it's prank. Maybe it's a couple of other things. Lots of different possibilities, but I'm pretty sure it's thank. And similarly, for the second gap, it's 70% sure that it's you, Y-O-U. But the word Y-E-W, which I think is like a kind of tree or something, is pronounced the same way. So maybe it's that. But in the training data, I've seen Y-O-U much more than Y-E-W, so it's probably Y-O-U. And then it gets to this third gap and says, well, in my training data, I know this shape means 4, F-O-U-R, the number 4, and I'm 70% sure that's right. But it could be 4, goo, true, any number of other things. And in this case, we know, since the sentence is "thank you for listening," FOR is actually the correct answer. So here the acoustic model gets it wrong. And then for some reason, it goes off the rails at the end and it says, well, this last word is glistening. It's probably not listening, it's glistening, which we also know is wrong. And that's sort of what the output of the acoustic model is. So the next step is the language model. And to clarify, when I say language model, I don't mean English versus Spanish versus Polish. I mean, just for the sake of this argument, English. We can talk about other languages later. But for just English, what kind of English? Are we talking about complete full sentences like you would find in an audiobook or an essay? Are we talking about an emergency phone call where the words are very short? Are we talking about radio audio where it's 10-4 codes like this, November, Bravo, Charlie, those kinds of things? You wouldn't see that in an audiobook necessarily. Or text messages, those are very different. That's what I mean by the language. And so when you are training a language model, you're training it purely on text. Acoustic characteristics, audio, none of that matters. You're just telling your model, this is the kind of English language that I'm going to expect to see in my calls. And so you train it on text. And what a language model actually does is it assigns probabilities to sequences of words. So one kind of language model, and there are many different kinds, but one of them is called an n-gram model. And what the n-gram model says, and I'll explain this one just because it's the most intuitive. What the n-gram model says is the probability of one word depends only on what the previous couple of words were. So for example, the language model is going to go through this sentence, which the acoustic model thinks is "thank you for listening." And when it gets to the word "for," it says, well, okay, what's the probability that if you started the sentence with "thank you," then the next word is going to be FOUR? That doesn't seem very likely. I've been trained on a lot of text, and I don't think I've seen "thank you for" very often. Much more common is "thank you FOR." So the language model says, I think that third word is FOR. But again, it could be any of these other words, but the language model thinks it's FOR. And then it gets to the last word and says, "thank you for glistening." No one ever says that. That's not a thing. So much more likely is "thank you for listening." I'm very confident that if the first words are "thank you for," this next word is going to be "listening." And so that's how the language model is adding to the transcription process. So at this point, we have the output of the acoustic model, which is a bunch of words and their probabilities. We have the output of the language model, which is a bunch of words and the probabilities. And we need to somehow combine these two things. We need to get them to play along because in the end, we only need one sentence as the output. And so basically what is done is all the different possible combination of words are combined together and tested one at a time. And technically, it's not all the combinations because some of them are not even worth testing. So it does it in an optimized way called beam search. But it tries a bunch of different combinations of acoustic model words and language model words. And it computes this function, which is called an objective function. And you do not need to understand what any of these terms mean. But at a high level, this first term is basically what the acoustic model thinks and its confidence. This second term is what the language model thinks and its confidence. And this third term is some extra penalty term that you get to prevent the model from just adding a bunch of words all over the place just to make sure it gets the right one. So don't worry about that. But there's an acoustic model term and a language model term, and we combine them together. And like I mentioned before, if the language model is very, very confident, then this term will dominate and it will be more important to the final sentence than the acoustic model. And vice versa, if the acoustic model is very, very confident, it dominates and the language model isn't so important. But the point is that this is the equation where acoustic model and language model are combined to figure out what the most optimal sentence really is. Okay, so that's a description of how the underlying transcription actually works. But what is equally important is identifying how well is it working? How accurate is your model? And so for other problems like image recognition, there are metrics like precision and recall, things like that. For transcription, it's a little more complicated, but not much. And the metric that is used basically in every academic paper everywhere is called word error rate. And this is an important metric to understand. So what the word error rate is it takes into account for a sentence, you have a transcribed sentence, but you also know the true sentence that it was supposed to be. It takes into account all the different ways that you got it wrong. You can get it wrong by substituting words that aren't there. So you replace listening with glistening. That's a substitution. You could just delete words, leave them out altogether. or you could insert words which aren't there at all. So thank you for listening, David. The David was not actually there. That's an insertion, so you got that wrong. And when you combine all those things and you divide by the number of words, you get a word error rate. And a small word error rate is good. You want a 0% word error rate. That means you nailed it. But a large percent word error rate means you got a lot of things wrong. So to build your intuition a little bit in this table at the bottom, maybe the true sentence is, hello, my name is David. Do you know what time it is? But if I try to transcribe that and I come up with, hello, my name's David. Do you know, N-O, what time it is? I made 2 mistakes there. So that's a word error rate of 25%. But the point is that if you just read this transcript, even with a 25% word error rate, you understood what I was saying. Yeah, the transcript wasn't perfect, but the point got across. And if you go a little further, and it's maybe the transcript I try again with a different model, which isn't as good, and it gets, hello, my name's Dave, you know what time it is. Now the word error rate's at 66%, and the meaning is starting to get a little vague. So big word error rate is bad, small is good. And every academic paper is always trying to get the lowest word error rate possible for their transcription models. But we are not academics on my team. We work in the industry. And what we are trying to optimize is not necessarily word error rate. And so when we communicate with the customers and we say, here's a transcript, here's a transcript, here's a transcript, which one is most useful to you? They don't necessarily pick the one with the best word error rate. They pick the one that's most useful to them. And so what my team is trying to do in the model training process is to figure out, well, if we're not going to necessarily optimize for the best word error rate, what are we going to optimize for? And that's some of the research that we do. And we figured out that, I think as was mentioned before, we do some keyword metrics. So for specifically the use case of emergency calls, some words are more important than other words. But this word error rate formula that I showed you treats all the words equally. If you get the word the wrong, that's just as bad as getting the word gunshot wrong or the words trouble breathing wrong. And those words are much more important than other words. So when we are training our models, we're not doing it just in a pure academic way. We're focusing on these words, which have come from customer feedback, because we are optimizing to make the most useful transcription product for the customers. Similarly, beyond keywords, other very important things in emergency calls specifically are things like spoken addresses. You really need to nail the address in an emergency call. If you talk to a call handler, they will say that is the most important piece of information in an emergency call. When you call 911, the first thing they don't ask, what is your emergency? The first thing they ask is, what is the location of your emergency? Address is everything. So when we are training our models, we are sort of biasing our training towards making sure we get the addresses correct. Okay, so we've talked about how the actual transcription works. We've talked about how to tell how well does it work. Now let's talk about how my team actually trains these models. And we train these models in a traditional supervised machine learning process. If you aren't familiar, what that means is you are handing the model these spectrogram images, which is sort of the data, and then you're also handing it the true transcript that was actually said. And generally, this is created by a human. And so when you hand this in a supervised fashion to the model, it's learning to correlate the two. And technically, the way that we do it is with a mix of open source software and third-party solutions and our in-house solutions as well. And we do the training on GPU machines, which we own and manage, but also with some cloud compute as well. And we have a team of research scientists and machine learning engineers and experts who are doing this experimentation, tuning model architectures and parameters, and most importantly, taking into account customer feedback. So the pipeline on the right here, going from the top down, the way that it generally works is that a citizen will call 911, which is the emergency number in the US. Our automatic speech recognition model will transcribe the call. My team and the CTO will collect the raw audio. We will have humans listen to the audio and transcribe, type exactly what was said to make sure the transcript is perfect. And then we use that audio and that perfect transcript to train new models, which we then deploy back to the customer. And so over time, as we repeat this process and we iterate, the models get better and better and more accurate. But if I were to just leave it at that and just say, this is a supervised machine learning process, this vertical column, I'm leaving out what I think is the most important point, which is off to the right here, is taking into account the customer and user experience feedback. So we have researchers customer researchers and designers who are interfacing with our customers on a regular basis and asking them, what is good about this? What is bad about this? What would you change? And that feedback comes back to our team, who then trains the models in different ways to optimize for that feedback. So that's the big picture. I will now hand off this presentation to talk about the actual deployment architecture and then an actual demo.
Yeah, thank you, David. So hello, everyone. I'm Maciej Rapsztyn. I'm working in Motorola in Krakow, and here we are developing currently the product which is called Smart Transcription, which is the practical application or practical use of the language and of the transcription engine that David was talking about. So first, the very quick look at the architecture. So on the left side, we have the PSAP, which stands for the Public Safety Answering Point. This is the source of our audio. From there, we got the audio streams. Typically, there are two streams per call, but of course, there might be multiple participants. So we will get multiple streams. The transcription service based on the metadata chooses the right transcription model, because we have different models for example, for different regions in the US with different accents, different wordings, and so on. So the actual transcription is made based on the transcription model. The audio and the transcript and the call metadata is stored in the DB database. And the live transcript, I mean the real-time transcript, is also displayed on the user screen. Also, the application, this is the web application, allows user to search for the historical data, and also the feature for supervisors that allows them to monitor all the calls that are happening at given PSAP. I will show you this in the moment during the demo. So let me now share my screen. Okay. And do you see my screen? Oh, sorry.
No, we can't.
It says it's loading.
Loading.
Okay, my Chrome froze from some reason.
Give it some time.
Okay. I hit share the tab, and it froze. Well, maybe I will try to reload the page, so I will need to reconnect most likely.
Okay, take your time.
Okay.
Maybe share your whole screen too, if that's possible.
But unfortunately, my Chrome froze. Okay, so let me. Maybe there will be some questions to David, and I will restart my Chrome, and I will get back. Okay.
Yeah. Sure.
Yeah, I can see that there are some questions.
For sure. So let's see. Okay, I don't think I've seen Sequest. Okay, how often do we train the model? That's a good one. Meaning asking how often do we compare human transcription with the model prediction? So how often we train the model, it depends on the customer needs and what sort of performance improvements we're seeing. Generally, when you're training a model and you are starting from scratch, the very first data that you provide to the model will have a very big impact in accuracy. It will help a lot. And so at the very beginning, when we started building this product, we were releasing models very frequently. And now we are continuing to collect so much audio and label it and train more that the improvements are tapering off a little bit at the moment. And so they're less and less frequent. But how often are we comparing comparing the true transcript to the inferenced transcript is something that we do very regularly, even if we're not doing it for training, because that's how you track how well is the model working currently. So for the customers, we're seeing how accurate the model is, and if that ever dips for any reason, then we know, okay, it's time to collect a bunch more data and add more and train more. So that's something that we monitor regularly. Okay, is the demo going, or should I keep going?
Mate, are you there?
We see his screen.
Yeah. Then Dave, keep on.
Going, Dave.
I'll be on. So how do you recognize pronunciation or sound quality? So sound quality is what the acoustic model is doing. And so maybe you mean like different dialects, different ways to pronounce certain words. There are different ways to solve that problem. You could have different models for different dialects. So maybe in southern the US, we have a different model in the northern US because they have different accents. Or you can just make sure that when you are training the model, it has been exposed to southern accents and northern accents. So if you make sure when you're deciding what data to use to train the model, you have a good balance of all of the different pronunciations and dialects to feed into the model, so it becomes robust and it becomes able to transcribe all of the different dialects. And those are the kinds of experiments that we are doing to figure out which of those solutions is optimal.
Okay, do you hear me now?
Yes.
Yes, we can.
Oh, okay, that's better. Okay, so here is the window of our application. Currently, there is no any call ongoing. So I will now play the audio and try to start the transcription.
Salt Lake 911, what's the location of your emergency?
Help, a man just kidnapped my baby. I was putting my bags in the trunk and he stole my car.
What is your address?
I don't know. I'm at Target.
It looks like you're calling from Target in West Valley. Is that correct?
Yes, the one in West Valley.
Okay.
Oh,
The address is 5518 High Market Drive, West Valley.
sorry.
Okay, please hurry. Save my baby.
Now it should
What
be
type of
visible.
car did they drive off in?
He stole my car. It's a gold Toyota Camry.
Okay, so the stolen vehicle is your car? Do you know the license plate?
I don't know. It's C something. C6 something.
Was it a Utah license plate?
Yes.
What direction was the vehicle heading?
I don't know. It just pulled out of the parking lot like I was heading towards the 201 freeway.
Do you know if he had a weapon?
I'm not sure.
Okay, tell me what happened.
I put my baby in her car seat in the back and started the car to turn on the AC. Then I was putting my bags.
Okay, let me talk about the application itself. So the call is still ongoing. We can see the phrases or the segments of the text which is transcribed, which the call is transcribed to. So you see that there are different splitted. The call is splitted per caller and call taker. We got the different avatars for them. So the call is presented like the typical Google chat or some messenger chat. On the left side, we can see the feature which is called keywords, which detects the predefined keywords inside the transcript. We have defined around 200 keywords, and that allows the operator or the call taker to quickly focus on the topic which call is about, what call is about. So in this case, we can see that there was phrases about the suspect, the stolen vehicle, the baby, then the kidnapped. So we can quickly grab the context of the call. The colors are according to the priority of the keywords. We have 3 priorities of the keywords currently, and also the operator can click on given keywords and it brings the portion of the transcript where these keywords occurs. Also, when there are multiple, of course, we can scroll to the occurrences. The we have some logic inside to two streams of the transcript. Typically we have two streams of voice, so we can two streams of transcripts. So we need to merge them together, basically according to the timestamp, but not always. We have the cases, for example, when there are overlapping segments, or where the one person is speaking very long. We have some logic to put them accordingly to make a logical conversation from that. Also, from the operators or call takers point of view, sometimes it's useful to have only portion of the information. We have the view like the call takers, callers only view, which means that the call takers is interested only in the sentences coming from callers, because he knows he or she knows what he's saying, but he can also check only the caller's sentences, or the view for the very small screens. I mean only the keywords view. From the other features, we have something like recent calls. These are only the test calls, that's why they are very similar, but these are the calls that were happening on this console, and the operator can check from, for example, from 12 hours time window, all the past calls. They can click of the one of the call and check the transcription of the past calls. Another feature is the history. History is history of the calls from the given number. So, for example, this is the number which we're calling, and here we can check all the calls which were made from the given number. And here is the monitoring feature. I need to start the call again. This is the feature for the supervisors. When on the PSAP, there are multiple console, of course, multiple positions, and multiple calls are ongoing. And in this view, the operator, the supervisor, can monitor many console at once, can see the context of the calls, can choose which is important, or which is which call taker needs help from some reason, or needs some assistance. Also, the supervisor can click on the particular calls. Currently, there is only one call ongoing, but there can be multiple. So the supervisor can just not listen to the call, but can click and watch the call, transcript of the call. And finally, we have the search feature. We can search the historical calls for many criteria, like call type, it was the emergency, non-emergency, or other, the call duration. Several criteria could be combined, like keywords. And also we have the free text search, which just searches through the transcript text. And when I click the search, or maybe because this is a test system, so maybe there are two, not, yeah. So for example, yeah, we got the results with the addresses, keyword, free text phrase. So yeah, this is how looks practical implementation of the transcription in our system. This is currently under the development, of course, but it is deployed to the customers, and the customers are currently using it. So I think that's it for the demo. Of course, any questions are welcomed.
Okay, so we still do have time for some questions. You can either write it down or just speak up if you want. I think that Dominic is typing something. So since Dominic has been typing something, I'd like to invite you all to our part 2 about the machine learning and artificial intelligence and how we apply it to fight against COVID. So we're going to send out a invite to another meetup that is going to take place in a week. So December the 2nd, feel invited. And I can see that there are questions popping up.
Yes, I can answer the most recent one. Does the model account for understanding who is speaking and therefore is able to follow the voice of the first responder? Yeah, so understanding who is speaking is essentially a separate problem, but is related. But the idea is if I train a model on spectrogram images of my speech, and I train the model on spectrogram images of someone else's speech, even if they're saying the same thing, the model can then learn who is speaking. In the emergency call handling product that I described, this actually isn't done because it isn't necessary on a phone call. It's just one person speaking and then the other person speaking back and forth. But you can imagine how this would be necessary for other use cases. Like if I have 5 people in a room and I just record all of them speaking on one microphone, I need to know who is speaking when person A starts and stops, when person B starts and stops, and the overlap. In the academic community, this is called diarization, and it's another technology that we are investigating both with open source solutions and custom in-house solutions.
If you scroll back up, there's a lot of questions during the during the demo.
Let's see, which machine learning algorithms do you use? All of them. we use, for transcription, there's a number of different ways to solve this problem. Recurrent neural networks, convolutional neural networks, even older networks. We experiment with all of the different ones. Does this speech with a bot or an operator? Oh, that demo was with 2 humans speaking on actual phone lines run through our actual system with our actual model.
Yeah, we've actually this has been deployed with real customers since March, and you can learn about it. It's called Smart Transcription, again on our Motorola Solutions website. We've literally done tens and tens of thousands of calls, and are deploying it around the country as we speak.
Yeah, of course, this system is scalable to handle hundreds of calls concurrently.
Yeah.
Are there any more questions? If not, I would like you to, I think that Tom is typing something, so give him one more minute. Maciej, so you're going to type, you're not going to answer that vocally.
Yeah, the last one. Yeah, I can also speak about the Tom's question about the training model. Maybe the David would be better, but I think the all trainings are done with the real 911 calls, acted ones.
Oh yeah, all of because like I was describing, if you need your acoustic model and your language model to work on emergency calls, you need to train them on emergency calls. You can't train them on something else and then apply them to emergency. Well, you can, but it wouldn't work very well. So it's all trained on real calls.
And a question about the Kafka or RabbitMQ. Internally, we are deployed in the Azure cloud, so we are using Azure services for the queues. So currently we are using Service Bus and Event Hubs from Azure services.
Yeah. Then there's another one. Can we later use pitch recognition to understand the emergency severity of the call? Yeah, understanding the severity of the call based on the words that were said and also how they were said is an important problem that can be solved with the same sort of technology. This is what a spectrogram image of somebody who is very stressed out looks like. This is what a spectrogram image of someone who's relaxed looks like. They will look different, and you can train the model to identify the differences.
Thank you, David. Thank you all. It was a pleasure. Like I said many times before, if you have any questions, just get in touch with us. We do have a direct email contact, and any question will be answered. It was a pleasure. And please remember, there is a part 1 next week. We're hosting another event. And to all of you based in the US and simply celebrating, have a great Thanksgiving tomorrow. Take care.
Okay.
Thank you.
Thank you.
Bye.
Thank you. Thank you all. Bye, everyone.